Okay, we're going to do this mass spring system. It's a great example of how to decouple a system. So we've got two masses on springs here. I'm doing the simplified version of this problem where both masses are the same mass and all three spring constants all have spring constant K. So x1 here represents my displacement from equilibrium. For mass 1, x2 is displacement from equilibrium for mass 2. So mass 1 is going to move over. If x1 is positive, spring 1 pulls back, and spring 2 pushes back. If x2 is positive, spring 1 would pull back, or spring 2, spring 3 would push back. So here are, using Hooke's law, here are my equations of motion. F equals ma, remember, and for Hooke's law, F equals negative k displacement. So this mass from this spring, the force, Hooke's law force, is negative kx1. This guy is pulling back if x1 is positive. Plus, if both masses move, this spring is attached to this mass. The amount this spring is stretched out is x2 minus x1. And if this spring is stretched in this direction, if x2 is bigger than x1, this spring would be stretched and would pull mass 1 over. That's why this is positive. So just simplifying here, we get this over here. Same thing for mass 2. Whatever this spring does to him, it's going to do the opposite to him. So we got this negative term here. Those are opposites. And then spring 3 here is trying to pull the mass over, mass 2 over. So we get this. If x2 is positive, the spring would try to push back in the negative direction. So we have a negative there. And simplifying, combining like terms, we get this. So dividing through by the m's, we get this system of second order linear DEs. Now we could do what we did in a previous video and turn this into, rather than a system of 2 second order, a system of 4 first order DEs. So I could make all of these substitutions. I got all these U's and V's all over the place. U1 is x1, U2 is x2, V1 is U1 prime, U2 is U2 prime, all this stuff. That would give me this 4x4 system. And I could write this out in matrix form. I got a whole bunch of zeros in here. I could find the eigenvalues of that matrix, find my 4 different eigenvectors, go back and solve for x1 and x2. It's really not even that bad because we have so many zeros in here. But an easier way to do this is decouple the system. If this said x1 double prime is some function of just x1, I could just integrate a couple times and be done. And that's what we're going to do. So we're going to decouple the system using these substitutions. U1 is the difference in the displacements. So if these guys, if U2 moves and U1 also moves over, if these guys move together, then this middle spring is not stretched. That's really what this is. This is how far the middle string has been stretched. So U1 equals 0 if these guys go together. If I say pull them both over the same distance together and let them go, U1 would just always be 0. U2 is how far this one plus this one have been stretched. It's the change in the center of mass. If I move these guys together, if I move them both apart, then x1 would be negative, x1 would be positive. The center of mass stayed in the center. So U2 is changing if they both move together, but it stays 0 if they move like this. And we call these the normal modes. These are the the periodic possible solutions to this system of DEs. If the masses move together, then the distance between them stays constant, or if the masses move together but in opposite ways, then the center of mass stays constant. And both of those are oscillatory behaviors and won't jump around. They'll be nice and simple. We'll call them normal modes. Okay, now it may be useful sometimes to resolve these in terms of x1 and x2. We're not going to use it here, but we could. So first off, if I add these two together, the x1s cancel. So I get 2x2 is that. So x2 is u2 plus u2, 1 over 2. Similarly, if I subtract the equations, I get x1 is u2 minus u1 over 2. Okay, notice, by the way, if I just take the derivative straight across, take two derivatives, u1 double dot would be x2 double dot minus x1 double dot, and similarly for u2 double dot. Okay, here are my equations again. I just rewrote them here so we could have them to see. Then u2 double dot should be these two added together. If I just add these two equations together and simplify, I get this. Check those details on your own. But that right there, that was u2. So u double dot is some multiple, some negative multiple of u2. And we know how to solve that. We want some function whose second derivative is a negative version of the original function. We know what that is. That's sines and cosines. So we get u2 is some cosine plus sine, where omega here is square root of k over m. We call that the angular frequency. And you should check that solution on your own. u1 double dot we get from subtracting these. This guy minus that guy. Check the details on your own. You get this, negative 3k over m times u1. Same idea, only now we get a different frequency. We get an extra square root of 3 in here, where omega is still square root of k over m. So this is my general solution. I could go back now using these equations, if I wanted to, and solve for x1 and x2. I really don't, because it's just a bunch of writing. What I really care about are these normal modes. So this guy says, if you start with 0 velocity, remember b here is going to be our velocity, our initial velocity. This says, who is u2? The x1 plus x2. If I separate these guys out some distance a, so this guy comes back a, he goes forward a, and I let it go, then these guys will just bounce back and forth with this angular frequency, square root of k over m. And it'll go like a cosine. This guy says u1 minus u2 also goes like a cosine, but with a different frequency. His frequency is multiplied by square root of 2. And that was if I moved them both over and let them go. The center of mass will oscillate back and forth like a cosine.